I'm sure many of you have seen this film, The Graduate, and there's this interesting scene where this kind of bit of a crazy uncle pulls away Dustin Hoffman's character and starts telling him something really important. Says he has just one word for him, and the world is plastics, because this uncle believes that there's a great future in plastics. And some of my friends think that I remind them of this crazy uncle because I have one word that I keep repeating, and in my case, this word is epigenetics, because I think there's a great future in epigenetics when it comes to aging. And here's why. Okay. Because it turns out that aging can be epigenetically reversed. And first indications of this were shown in 2006 by Shinya Yamanaka, the Nobel Prize-winning scientist, who discovered that these four factors, OSKM factors, which were later named Yamanaka factors, can actually epigenetically return a cell back to its essentially embryonic state, pluripotent state, where it is age 0 for a cell. And it's also physiologically rejuvenated while it undergoes this process of reprogramming. And later on, in 2016, a group of Juan Carlos Espiso and Belmonte, who got a shout out yesterday, they showed that these Yamanaka factors can actually be triggered in vivo, in an animal. And in doing so, they can also rejuvenate the organism and prolong its lifespan. And this is the study, this groundbreaking study that was published in 2016 by Alejandro Campo and others out of the Belmonte lab. And they showed, if you look at the graph on the right, the survival curve on the right, that the mice that underwent this epigenetic rejuvenation therapy, they lived up to 50% longer. So there are 3 control groups on the left and the therapy group on the right. Now, mind you, these are progeric mice. They have very short lifespans, but still, this kind of first proof of concept that this can be done safely, I think it's remarkable. And this is what inspired me to start Ethereum back in 2017 to translate this therapy into something practical that we can all use for ourselves for radical life extension. Why is this even possible? Why is epigenetic rejuvenation possible? Because it turns out that we're lucky that the cellular reprogramming happens gradually. It's not like a skin cell just jumps back into becoming a pluripotent embryonic cell. It does so gradually while being rejuvenated in the process. And this kind of inspires us that we can find the therapeutic window in which it is still, the cell doesn't lose its identity, it is still a skin cell, but it is remarkably rejuvenated while remaining the skin cell that it started with. So there's this slide that shows this gradual process, and it has become very popular as the format has shown the slide a number of times. Michael West also uses it in his presentation. This is just a graphical representation of what is happening while the reprogramming is going on. So as OSKM genes are being induced, the epigenetic age, the blue line, gradually decreases, while cell identity also decreases gradually. So potentially this narrow blue window, if we can hit it repeatedly, we can enjoy rejuvenation without losing functional status of the cell. And this is kind of the holy grail that the epigenetic rejuvenation companies are now trying to explore. And thankfully, it's not just us these days. There's several companies that have entered this field since 2017. I think the first one was TurnBio out of Stanford, out of the lab of Vittorio Sebastiano, and his student Jay Sarkar, who in 2015, I think they published a paper, Rejuvenation on the Road to Pluripotency, which showed this proof of concept that this is possible. And then, of course, the Belmonte paper came out. Now, all of these companies exploring epigenetic rejuvenation, they all have subtle differences. For example, TurnBio, they're focusing on, first of all, they use 6 factors, not just Yamanaka, but also 2 other factors. And they're looking at ex vivo rejuvenation. And also they want to use not genes, but mRNAs, which is, they think is a safer approach. Then, of course, there's David Sinclair, who's now, I'm sure you've all heard, is now also exploring this epigenetic reprogramming approach, off from his NAD. And they're using 3 factors, OSK factors without the MYC. But now they're using actual gene therapy. They're using AAVs to deliver locally these Yamanaka genes in the
places of interest. For example, into the eye, they want to rejuvenate old eyes and maybe fight glaucoma, and also trying to rejuvenate nerves in case of paralysis. And they're saying they will enter clinical trials maybe as early as next year. For this, they formed this company called Iduna, or Iduna. Iduna is the Norse goddess of rejuvenation, just a piece of trivia. And he kind of attracted all the heavy hitters from the field, starting with Juan Carlos Esquizo Del Monte, Steve Horvath, and Manuel Sorano, who was also one of the pioneers of in vivo reprogramming. And so they're exploring that paradigm. Also, there's Michael West, who I'm sure you all know very well. Now, out of Ajax, they've spun out this reverse bioengineering company that will focus on this epigenetic rejuvenation approach, probably using the small molecule cocktail, but I'm sure Mike will tell you much more about it tomorrow while he will be speaking. And finally, this is us. We will pursue actual in vivo gene therapy. We would like to get the necessary genes into the organism, and then these genes will be normally silent until we activate them with some kind of inductor. Right now, they use doxycycline, which is used in many models to activate these genes, but we really want to move away from an antibiotic, something more inert, or maybe even a novel patentable molecule. And PETs are a very interesting strategy for us because they provide an opportunity to circumvent the delivery problem. Because of course you have to get all the genes into the cells of an organism, and for an adult, you need to target trillions of cells, which is an issue in itself. But if you can do a GMO PET, a transgenic PET, into which you insert those genes while still in embryo, those genes get copied into all the cells of an organism, and you can activate them and experiment on the PET, seeing what kind of life extension it can obtain from using these genes. So when can you expect these therapies? For GMO animals, within 5 to 6 years, if everything goes according to plan and we don't have any kind of setbacks, maybe safety issues. And then for existing animals, genetic therapies, we approximate that within 8 to 10 years you'll be seeing it on the market, and for human therapies it will probably take another 8 to 10 years. So just one parting word from me. You guessed it, epigenetics. There's a great future in epigenetics, so just think about it. Thank you.